Hello everyone. We will now look at affine varieties locally. So remember, we have defined affine varieties as ringed spaces that are isomorphic to the ringed space of an algebraic set. So essentially we are looking at algebraic sets, but now we want to investigate behavior at a point A in an arbitrary small neighborhood, and we want to investigate properties that should depend on a point A but not on any other point. The problem is the only thing we have access to are the open sets of our topology, which can be quite big, but in general we want to somehow from these open sets get to the smallest possible open set, whatever that means. The idea that we use is that of stalks and germs. So this can be generally defined for a pre-sheaf on a topological space X. So if you have a topological space X and a pre-sheaf F, then the stalk of F at the point A is the following. You start with the set of pairs consisting of an open set containing A and some section of F on this open set. But not just that, you mod out with respect to an equivalence relation, where you consider two such things equivalent whenever they agree on some open subset V containing A. That is important. And the elements of this thing are called the germs of F at A. So what does this mean? Morally, if you think of these sections as functions, then you are looking at functions defined in neighborhoods around A, and you consider two such functions as equal if they are equal on some open set containing A. Meaning that if they are equal except for at a different point, since points are closed as far as we have considered so far, excluding that point will give you a smaller open neighborhood around A. And so the behavior of your functions at this other point will not matter. So you're looking at the local behavior at, so to speak, the point A of functions. So as an example, let us look at the affine variety x equals a1 with a equal to 0. So we want to study things locally at the point 0. Then remember now, if we look at Ox of u for some open set u, these are locally functions that are locally of the form g divided by f, where f doesn't vanish on u. So the stalk of regular functions at 0 will somehow be the functions that are written in this way with f not vanishing at 0. If f vanishes at any other point, you can just exclude that point. So f is a polynomial in one variable, so it will only vanish at a finite number of points. Of course, it cannot be identically the 0 polynomial. And so you just remove these points and you get functions, rational functions that do not vanish at 0. That is the moral of the story. And to better understand these objects, we need the notion of localization from commutative algebra. So if you have not watched the video on localization, this is the time to stop and do it and come back to this video when you have watched that one. Equipped now with the machinery of localization, we can study these stalks that we just defined. So we are in the situation where we have an affine variety X with structure sheaf OX and a point A in X, and we want to understand the concrete structure of these stalks, the stalk of the structure sheaf at the point A. And instead of denoting this O sub X parentheses sub A, usually this is denoted O sub X comma A. But before we do that, let's look at another instance of localization that is in many ways easier and that uses a different kind of localization, not at a prime ideal, but at a point. Namely, we want to consider the regular functions on principal open sets. So remember that if we have an algebraic set and a function, a regular function on this set X, then we looked at these principal open sets, which were the sets of points where f did not vanish. And the claim now is that the ring of regular functions on UF is the localization of the ring of regular functions on X at this element f. So what does this mean? Well, remember that from before we know that the ring of local functions, we have shown that this is the set of all g divided by f to the power n, where g is in OX of x. And this localization, as you saw in the localization video, this is the ring where we have inverted all powers of f. So this is the set of all g divided by fn, where g is in OX of x. So at a first glance, it seems that, yes, obviously these are the same thing, so there is nothing to prove. But one has to be careful with what quotient means. Here, quotient means as an equivalence class in the definition of localization. So equivalence class in the definition of localizations. So in this, if I call this ring R, I am in RF. Whereas here, this quotient is just the function that maps an element x to g of x divided in the field by fn, power n of x. So there is an obvious candidate of a map. So we want to define a map that goes in this direction and maps the formal quotient g divided by f to the power n as an element in the localization to the function quotient g f to the power n. So this is well defined. That's the first thing to check. Why is that? Well, if g divided by fn is equal to g prime divided by fn as functions, as elements in the localization, well, then we need to show that they map to the same thing, to the same function. So what does it mean that they are the same in the localization? This means that this difference, g f to the power n, this doesn't have to be the same n, it can be some m. So g f to the power m minus g prime f to the power n becomes 0 when you multiply it with some power k, with some element in the multiplicatively closed set. This wasn't the definition of localization. Note that on UF, this thing is not 0. This is how UF is defined. So this is never 0 on UF, and therefore this has to be 0 on UF, and therefore they define the same function on UF. So then they define the same function on UF. That's the important non-trivial part. And now that we know it's well defined, well, we need to show that it is surjective and injective. And surjectivity is clear because we know that we have seen before that these are all the regular functions on this set. And to show injectivity, well, we simply do somehow the same thing. So if g divided by fn is mapped to 0, so if g divided by fn is equal to 0 as functions, then what does this mean? This means that g is equal to 0 on UF. So gf is equal to 0 everywhere. So gf is identically 0 because outside f, that's where f is equal to 0. And from this, you conclude that f times g times 1 minus 0 times f to the power n is 0. And this precisely says that, or precisely implies that g divided by fn is equal to 0 divided by 1 in the localization. So this indeed does define a bijection, and you also assume that this is a ring homomorphism, which is easy to check. Then it is indeed an isomorphism. So these two things are the same thing. Now let's go back to our stalks. So you look at the affine variety X with structure sheaf all X, and you look at a point A, and remember, as we have seen, that I of A is a maximal ideal, so it's a prime ideal in OX of X. And the claim is that the stalk OXA is isomorphic to the localization of the coordinate algebra at the prime ideal I of A. So what we need to show is that we have an isomorphism of rings between this localization and the stalk. And so what do? We take a formal quotient and map it. So remember, the stalk consists of equivalence classes of pairs where we need to specify some open set. So I'm going to take the principal open set with respect to f, and I'm going to take this function. So we need to show that this is a ring isomorphism. It's an exercise to check that it's a ring homomorphism, supposing that it is well defined. So why is this well defined? Well, if g sub f maps to, well, is the same, I should say, as g prime divided by f prime in this localization, then this means by definition that there is some h such that this product is 0, where this h is in the multiplicatively closed set. So for some h not vanishing at A. So this means that in the intersection of UH with UF and UF prime, this is an intersection that contains our point A. These functions in the parentheses are the same. So meaning that the functions agree on a neighborhood of A. So here you have g divided by f is equal to g prime divided by f prime. So they map to the same thing in here. So this is well defined. And surjectivity is more or less by definition, because any function in the stalk is of this form. If it is injective, you play the same game as on the previous slide. So in this case now you assume that g divided by f defines the zero function on some open neighborhood of A. And because all open sets are unions of principal open sets, you can shrink this to a principal open set. So assume that this is 0 on some open set defined by H, with again H not in I of A. Then if you multiply G by H, it will vanish on all of X because you're looking at the principal open set. So writing this as HG1 minus F times 0, you get something that is 0 everywhere. And so this means that indeed G divided by F is 0 in the localization. So again, the notion of localization now with respect to the prime ideal corresponds to the thing we want in geometric terms. And so as a corollary, the stalk is precisely the So as a corollary of this, we get a precise description of this stalk. Namely, it is the set of all quotients where f and g belong to the coordinate ring of X and f does not vanish at 0. This was what I was hinting at when we considered the example of the line at the point 0. Now we have a precise description of this. And so since we have localized with respect to a prime ideal, this should be a local ring. And it is indeed a local ring, and the maximal ideal is the set of all functions vanishing at this point. So described in this way, the set of quotients g divided by f, where f of a is not 0, but g of a is. And this motivates the name of local ring. So when you have the stalk of your sheaf at the point A, this is a local ring. You consider all the functions that are defined arbitrarily close to and at A. And the maximal ideal are those functions that actually vanish at A. And this shows the importance of the point A in the stalk, and showing that the stalk indeed depends on A alone somehow.